Today we're going to be talking about Snell's Law. Now we've already seen Snell's Law, and what we're going to do today is actually what we call the Brachistochrone Problem. What's the Brachistochrone Problem? Brachistochrone is two Greek words, brachistos, which means shortest, and chronos, which means time. So you put them together, and Brachistochrone means shortest time. So we're going to be doing the shortest time problem. And the shortest time problem, there's lots of different shortest time problems, but the shortest time problem, the Brachistochrone, is the one we're going to focus on. But I'm going to start with going back to Bernoulli in 1696 because it's just kind of interesting getting how it started and how this is important to physics. So, and obviously, you know, on the test, I'm going to ask you actually about all of this history stuff. When I was in college, I thought it was ridiculous. The teachers covered their history stuff, and I took the GRE and had all these history questions of physics, and I was really angry that I hadn't paid attention. But the understanding how we get to where we are is important to helping you understand how things are applied. So what Johann Bernoulli, I said Joseph before, Johann's brother, I suppose you'd say Jacob instead of Jacob, I don't know. Anyway, the Bernoulli brothers, Johann looked at a problem that Galileo did wrong. Galileo said that if you want to get from point A to point B, with gravity being the only thing that's acting on you, the shortest path is going to be a circular arc. So basically, what Galileo said was, if I want to get from point A to point B, and the only thing acting on the object is gravity, that I should just have myself a nice little half or a quarter circle there. And it's easy to see why one would think that makes sense. I mean, it generally seems right. As you drop down, it speeds up. But you don't want to have just an L, right? Because when you hit the bottom, it wouldn't have any horizontal velocity, so you need to have something to change the direction. And if you had it come down and had a sharp curve, that would be a longer distance, and longer distance, even at higher speed, takes more time. You know, so you have a competition between the distance and the speed. And so it seems like circular arc's a good answer. But that was incorrect, and Johann Bernoulli had solved the problem. He knew that Galileo was wrong, and so he published his little riddle, putting in some words to tweak Isaac Newton. And so, you know, he publishes this, you know, here's this thing, see if you can do it. And he said something about, yeah, that's where this is. I knew I'd brought the charger. You know what was wrong with my quadcopter? There was hair wrapped around one of the little motors. And Seth said, you know, if you pull off the rotor, you can pull the hair off. He was right. So it's all working again. Anyway, back to this. There's only the three of you in the class? Yeah, okay. I'm taking a class with. Okay, so back to this. So he kind of tweaked Newton, and so Newton sat down, and he came up with the solution of a cycloid, as did a bunch of other people. You notice that Johann's brother came up with the solution. Leibniz came up with the solution. Who's Leibniz? Yeah. Leibniz is the other one with the claim to inventing calculus, the one that came and had Newton explain it to him and then published about it. And you can, once again, from the way I describe it, you can see who I give the credit for creating calculus. But Leibniz made a solution, and L'Hopital, I put L'Hopital's full name. Life was complicated back then. Guillaume Francois Antoine Marquis de L'Hopital. They all came up with these, and Newton said, you know, he just did it overnight, went home one night, worked on it, submitted it the next day. And then he said he did not appreciate being pestered by foreigners about mathematical things. Because of the little tweaking words, he felt he had to do that to maintain his reputation. But he didn't appreciate, you know, being pestered. So he wanted them to know, yeah, I can do it, but come on. So we're not going to go through this solution, but what this did was it started setting up the idea of optimizing for time. Brachistochrone problems. And so, that's lovely. There are words here. So Euler developed a method of variations, varying your path to give you the shortest time. And then Lagrange polished it up in 1760, and he developed what we call Lagrangian mechanics. We have the Lagrange equation of the first order, which is the one I didn't show. The second order is the one I did show. The second one is also called the Euler-Lagrange equation. Euler for, you see up there, E-U-L-E-R, that's Euler, who developed the theory of variations, and then Lagrange, who did the final work. And so the mechanism, now I actually need to brush up on this myself. It's been a long time since I've done the Lagrangian work. I remember it being super easy and super useful when I was in college. But the Lagrangian, this thing here is called the Lagrangian, is just the kinetic energy minus the potential energy. And you use generalized coordinates. So the Q is a generalized coordinate. In other words, Q could be X, Y, Z, theta. It could be, it's a variable that has position in either linear space or rotational space. And then, of course, when you put the dot over the top, what does it mean to have the dot over the top? The first derivative with respect to time. So you have your Lagrangian is a function of position in all of your different variable space. So in a complicated problem, you could have X, Y, Z, theta 1, theta 2, theta 3, right? Whatever your position variables are. And then the derivatives of those, generally your kinetic energy depends on the derivatives of, the speeds, in other words. So the Q dots we call the generalized velocities. And then you just have a simple equation that's a differential equation. And I love that it has partials. Why do I love partials? They're easier to work with because anything that isn't that variable, you just toss. So a partial of L with respect to Q, let's say that my Lagrangian just depends on X and X dot. If I'm doing the partial with respect to X, X dot is a constant. And likewise, if I'm doing the derivative with respect to X dot, X is a constant. And so it's pretty simple doing the math. And then it gives you a set of equations that often are already uncoupled and you're done. So it's a way of solving problems that is using the energy method. Remember, we learned a force method, then we learned an energy method. This is a variation on the energy method. When we get to quantum mechanics, which is coming up really soon, we'll have the Hamiltonian equation. The Hamiltonian is another variation of this method of variations. It's similar to the Lagrangian and how you do Hamiltonian mechanics, and that's what they use in quantum mechanics. So the Hamiltonian is, again, using a variational principle like this. Well, how does that get us to our optics problem? Fermat, famous for Fermat's last principle, the one that he had written in the margins that he died before he had time to actually write out a proof. He just wrote in the margin, I have found a very unique proof that this is true, and it's some crazy, I don't remember the equation. And it has been solved now. When I was in college, it was like the grand problem all mathematicians wanted to tackle.
I thought you said something like proof is easier in the margins or whatever.
Yeah. Well, I thought it was I have a simple proof, but yeah. And yeah, everybody assumes that while he was right, he made a mistake because it's not simple. So Fermat proposed that light takes, it's underlined here, let me make it now highlighted. Light takes the path of shortest time to go from point A to point B. Now, we saw before that the circular arc that Galileo said was not the shortest time for something acting under the force of gravity alone, it was a cycloid, part of a cycloid was the answer. Now we have Fermat saying that light should take the path the shortest time. So now if we think about this, we started in light by saying we're using a ray problem, right? Light travels in rays. And if I say, okay, what path going from me to Nate is going to take the shortest time, which path would it be? Okay, straight line. Because we all learned when we were kids probably the shortest path between 2 points is a straight line. And if we have a constant speed, then the shortest path will correspond with the shortest time. But if there was something, between us, it might not be the shortest path that gives us the shortest time. If there was something that, a wedge of plexiglass that's angled like this, and he's in the plexiglass because apparently he's been bad and Jabba the Hutt has put him in storage, then it's not going to be the straight path that will get to him the quickest. And Fermat said it's going to be the path that's the quickest is the one that the light's actually going to follow. And so it's the Brachistochrone problem. It's the one that we're looking at here. And so that's what we're going to do. We're going to find that path and see that it predicts Snell's law. Now, this is, just a prediction by Fermat. It wasn't based on actual anything except for it made sense to him. So this isn't a proof of Snell's law. What, in fact, it shows is simply that Fermat was right. It's a proof that Fermat was right. So let's go through the work. This is the last slide. I should probably add right now additional slides because I'm going to need them. Page manipulation, insert. It's not going to work. So we close that, and then we do insert again. And now it's going to work, and I'm going to put in 2 pages just to make sure I've got all the pages I need. So here we go. This picture, come on. Okay. Now the app is failing, but everybody knows now what we have to do if the app is failing. We just close it, start again. You know that by now, right? You see me do it multiple times. Makes you wonder about the robustness of the app just a little. Okay, so this picture illustrates nicely the problem that I was talking about here with the light going from me to Nate. Here we have a lifeguard. And we have a drowning swimmer. And the lifeguard, I'm going to save you. And the lifeguard wants to get to the swimmer as soon as possible so as to get there before the person dies. How many people here are lifeguards? Just one? Well, if you're actually, are you two? No. If you're a lifeguard, you learn important things like, if at all possible, don't touch the person. Because what is the person going to do if you touch them? Yeah, they're panicky. They're not thinking, oh, this person's going to help me. They're going to think, if I just push them under, I'll be up higher. And so lifeguards can be drowned if, the person comes. Second thing you do is, you come out and you try to stay your distance and entice them. You tease them. Okay, this way, and just have them lunge toward you. If they pass out, then you can rescue them without problem. Third thing is, okay, I don't know why I feel compelled. Let's suppose that this young lady is drowning, and so she has passed out. What do? I reach across my right hand to her right hand, and I grab and I flip her over and drag her that way, right? And if she's not unconscious, well, then I'll probably have to be a little more careful and pull her in and lock her down. You lock them down so they can't fight with you. Like pull them in. Okay, so that's what you're doing here. You don't want to get to that part of actual contact. That's why they have things like, see, he's got, I don't know, they want to call it a can. I don't know. We just called it a flotation device. You throw that out there and you can have them hold on to that and then you can swim them in. You don't have to touch them. They can't drown you. Okay, so just getting the realism out of the way. We have a swimmer that wants to get there as soon as or a lifeguard that wants to get there as soon as possible, and we have multiple paths shown. So we have the path of shortest length is shown in Aqua. And we have the path with the most time in the water, or the most distance in the water, least sand, and the path with the least water and the most sand. None of those are the fastest path. Now, of course, start with the logic. Where does he go faster, in sand or water? Sand. So it seems like you'd want to maximize sand. Of course, that doesn't mean you run 5 miles down the beach and back because you got more sand time. Right? You want to maximize within the confines of getting there quickly. And so you want to minimize the water time, but if you went absolute minimum water, you went too far in the sand and you lost time. And so we have to optimize it. So the optimal path is going to have longer than the minimum necessary in the sand, but shorter than the minimum necessary in the water. And we have to use actual calculus to find what the path is. So then let's look at our picture. So here's a picture to guide us. So we have P, that's where the lifeguard stand is, where the lifeguard starts. P prime, where the person he's going to get to is. And just some variables to make life easy. A is the distance from the shoreline to the lifeguard stand. B is the distance from the shoreline to the drowning person. And X will be the distance from the normal. Hey, oh yes, I'm on highlighter, that's why. From the normal to where he enters the water. And D is the distance that's parallel to the shoreline from where the lifeguard stand is to where the person is. So D is the only thing that's not marked here. That is, believe me, that was a D. That's a better looking D. So there we have our variables. What's the point of this? We want to find what path is going to be the quickest. So everyone here is taking calculus. If I want to minimize something, what do? Take the derivative in, set equal to 0. So I need to have a function that I can minimize, a function that I can take the derivative of and set it equal to 0. Now there's something that we didn't mention in that. I want to minimize in terms of time, so that means I need a function for his path as a function that gives me the time for his path, and then I'm going to need to take a derivative with respect to a variable to minimize. So I need an equation to tell me the time it's going to take for a given path. Now we've already established if you have a constant speed, the shortest time is a straight path. So that's why we have our answers straight paths, one in one material, one in the other. How do I find then the equation for the time it takes to go from point P to point A to point P prime? So find equation for time is the first step. And then we'll take the derivative after that, but I want to find this first before we go on to that. So how can I find equation for time? I want you to work your way through it. Okay, time is equal to distance over speed. That's a definition, right? If you have a constant speed, then distance is speed times time, so time is distance over speed. So that means that I have time 1 is equal to distance, and since I use D, I'm going to call it L1 over V1. And time 2 is equal to L2 over V2. Now I need to find L1 and L2 in terms of the same variable so I can take the derivative to minimize. What's the one variable that I can use to find both L1 and L2? X, right. Why I called it X in the first place. So what is L1 in terms of X? It's the square root of a squared plus x squared. And what is L2 in terms of x?
B squared plus b minus x over b squared.
Bueno. So I have L1 and L2. So I can put these in, and I have my total time is equal to T1 plus T2 is equal to L1 over V1 plus L2 over V2 is equal to square root of x squared plus a squared over V1 plus square root b squared plus d minus x quantity squared over V2. There in the final form, I have my time as a function of x. So now we go on to step 2, as was already indicated by Carrie. Take derivative of t with respect to and set equal to 0. So dt dx is equal to, derivatives of a square root. Basic rule. Derivative of a square root, how do you do that? Do what? Okay, it's the object or the argument, that's the right word. The argument raised to the 1/2 power. And so since it's raised to the 1/2 power, I'm going to bring down the 1/2. So there's bringing down the power. And then I'm going to have it lower the power by 1. So 1/2 minus 1 is minus 1/2. So on the bottom, I'm going to have that same square root. Now I'm going to just be a cheating cheater here and say, well, that square root term was L1. So I'm going to make life shorter and just write L1 on the bottom. I know L1 is a function of x, and it's shorter to write. And then I have to have the chain rule. My argument wasn't x, it was x squared plus a squared. So with the chain rule, what do I have to do next?
Take the derivative.
Yeah, take the derivative of the inside. So the derivative of x squared plus a squared is 2x. Now I can't forget that there was a v1 in my equation. In preparation for today's lecture, I forgot the v1. You can't solve the problem without that. Okay, so there's my first one. The second one is going to be the same process. So I'm going to have 1/2 L2 on the bottom. Derivative of the inside is going to be, I get to use the chain rule twice. D minus x, I brought down a 1, you don't see it. And then times minus 1 for the derivative of the inside of d minus x. So that was the chain rule twice. And I needed 2. And again, can't forget that it had the v2 down there. Now I take this, I evaluate it at x sub 0. X sub 0 is going to be the x that gives me the minimum time. And so I better put sub zeros on each of my x's here. And so that should equal 0. So simplifying this equation, you notice the 2's cancel. So those aren't going to concern me. And I have 1 over v1 times x sub 0 over L1. Because of this minus sign, it's going to be minus d minus x0 over L2. And I forgot, I wanted to put out front 1 over v2. And now I notice something cool. x0 over L1. Going back to my initial picture, what is x being this distance, divided by L1? Or to make it more obvious, this distance here is x0. What is x0 over L1? It's the opposite over hypotenuse, which is sine of theta 1. So this becomes sine of theta 1 over V1 minus d minus x0. D minus x0 is this distance right here. So d minus x0 over L2 is sine of theta 2. Now, am I at Snell's Law? Yeah, I pretty much am. What do I have to do to make the Snell's Law? Only two things. I will first, let me change color. I'll first multiply everything by C. Why do I do that? Because N is defined as C over V. So since I multiplied everything by C, then C over V1 is N1. C over V2 is N2. And then the final step is moving the negative one to the other side of the equal sign. And so I have there I did them in opposite order that I said. And there we have found that Fermat was right, that Snell's Law, how is Snell's Law really derived? It's really derived doing geometry. It's really derived by taking the wavelength. I showed you the picture in class, but I didn't actually do it. Taking the wavelength in each material, because the wavelength changes. If you go into a slower speed, the wavelength is shorter because it travels less distance in the time to do one cycle. And that was how Snell's Law is actually derived. But now using this variational principle, we're able to show that Fermat was correct, that the path that light takes to go from point A to point B is indeed the path of shortest time. And speaking of shortest time, I'm done. Any questions? Yes, Aaron.
I'm sorry, I missed why you multiplied by C.
I multiplied by C so that I could replace the variables V1 and V2 with the variables N1 and N2.
It's there on the side.
Well, the definition is here, and then the application is here because I actually put in, 2 extra pages. I didn't use either of them like I thought I would, but I ran out of space on this one. For one line, I didn't want to go sully up another page. Other questions? So when it comes to the next test, for this lecture, you could be asked to basically show what I did here. Show that the path light takes, that Snell's Law predicts that light's going to take the shortest path. Right? Because when you got down to it, the work wasn't hard. You just had to remember things about your calculus and going back to the simple kinematic equation of distance is speed over time. And remember that, well, if it says show us the short path of shortest time, that means you're going to have to use the optimization.